Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to power systems engineering. So in this video we'll be discussing about the magnetic field due to conductors from the point of view of conductors and transmission lines and in any other aspect related to power systems engineering. So we'll be sticking to only the basic concepts and formulas without going deep into the derivation part. Previous video we covered the electric field due to conductors, so please check out that video first and then come to this. So first, the very basic thing, magnetic flux and flux density. So basically magnetic flux, it is a measure of the number of magnetic field lines passing through a imaginary area. Okay, so the magnetic flux can be determined by the dot product of the magnetic flux density B vector, magnetic flux per unit area, the imaginary area, and the area vector. And if they are at a particular angle, so that gives us this cos theta part. Okay, the dot product of B vector and A vector. So here maximum number of magnetic field lines, they pass through it when this theta angle is 0. In that case cos 0 will be 1. Same for electric flux also, where electric flux phi was Ea cos theta, here it is Ba cos theta. There it was E vector dot A vector, dot product of electric field intensity and area vector. Here it is magnetic flux density and area vector. Now here the unit of magnetic flux is Weber and flux density is Weber per meter square or Tesla. Both are acceptable. Next is Biot-Savart law, which gives us the magnetic flux density at any point away from a particular conductor. Okay, conductor which is in the form of a wire. Here we are considering that. So let us say we have a current carrying element XY, it carries a current I, and we pick one small current element. Okay, here we have picked a small current element dl. So the current element is signified as IDL vector. This current element, it is at an angle theta. If we draw a tangent at this point, it will make an angle theta with the straight line connecting this current element and the point P, where we want to determine the magnetic flux density. So Biot-Savart law, it gives us an expression of this magnetic flux density. So how we determine the total magnetic flux density to the whole wire? We divide each of these portions into small current elements. Each of these portions in small current elements. We determine the small magnetic flux densities due to each of these current elements and then we integrate it to get the total. So here for each of these portions, the magnetic flux density at this point P is given by the formula dB is equal to K ideal sine theta by R square. Okay, dB is equal to K ideal sine theta by R square, where dB is the magnetic flux density due to small current element ideal. Here K is given by mu 0 by 4 pi. Mu 0 is the absolute permeability of free space, and if it is in any other medium, the relative permeability will come into play. Mu 0 mu r, that. So that is equal to 10 to the power minus 7 Tesla meter per ampere. Okay, and this is in scalar form, and if you want to express it in vector form, this will be given as mu 0 by 4 pi I dl vector cross r vector by r cube. Okay, so this is the expression. So here as you can see, this is the cross product of the current element vector and the radial distance, distance of that particular element from the point where we want to determine the magnetic field. So dl vector and r vector, they are in one plane, and the resultant magnetic flux density, that will be in the mutually perpendicular direction to that plane, perpendicular to the plane where dl vector and r vector are contained. That is the rule of cross product. So please check the basic physics playlist also, where we have discussed everything related to vectors. So the next concept is Ampere's circuital law. So it is kind of similar to Gauss law in electrostatics. It is the magnetic version. That is the electrostatic version. This is the magnetic version. So here it is said that, let us say we have a magnetic area in a magnetic field, a conductor which produces a current carrying conductor which produces a magnetic field. So here this conductor, it is carrying a current I, and as a result it is producing a magnetic field like this. Now we know that by right hand fist rule, a straight current carrying conductor, if the thumb points in the direction of the conductor, then the direction in which the fingers are curled, that gives us the direction of the magnetic field. So here the line integration of this magnetic field, okay, the line integration of this magnetic field is mu0 times the current which is enclosed by that magnetic field. So simply here the line integration, the closed line integration of the magnetic field, that will be equal to mu0 times the current enclosed by that field. So here only one current carrying element is enclosed, so this is mu0 I. Appropriate definition would be B vector dot dl vector into mu0 into I net, the total number of current carrying elements. So here there is only one current carrying element, that's why mu0 I. So this is the formal expression of Ampere's circuital law, which is the line integration of a magnetic field around any closed path is mu0 times the current enclosed by that path, that magnetic field path. This is the statement. Mu0 is the absolute permeability. This is very much similar to Gauss law of electrostatics, where the electric flux phi E, that is the dot product of E vector dot A vector, which gives us the 1 by epsilon 0 times the net charge enclosed by that surface. Okay, integration of this is E vector dot dA vector. Okay, this. Okay, so this is the Gauss law in electrostatics, and this is Ampere's circuital law in magnetic field. Now we will focus on magnetic field due to different types of conductors. So let us say we have here the magnetic field due to a long straight conductor. So let us say we have a long straight conductor XY which carries a current I in the upward direction here, and we want to determine the magnetic field, magnetic flux density at a point P. So here what we'll do, the process is we connect each of these two ends of the conductor by drawing lines from these points X and Y, the two ends, to the point P. So here the point X makes an angle phi 1 with respect to this point P in the horizontal direction, and the point Y makes an angle phi 2 with respect to P in the horizontal direction. Okay, here QP is equal to A. So here what we'll do, we'll proceed from one end to the other from X to Y, dividing this whole conductor into small portions. So here, as we have seen, we have taken a small portion L, and we go from this point to X to Y, dividing it into small current elements. Here we have taken this small current element here, this one IDL, and this small current element, it makes an angle phi with respect to P. So by doing that, we get the expression for magnetic field due to this long straight conductor. We are not going into the derivation part. So that is given by mu 0 I by 4 pi a into sine phi 1 plus sine phi 2. So here a is the distance between the midpoint of this conductor and the point, sorry, not the midpoint, the line joining the point where we want to determine the magnetic flux density and where it touches the conductor, QP. Not the midpoint, this is not the midpoint, okay, my mistake, I said it is this, okay. So next is the magnetic field at the center of a current carrying coil. So let us say we have a coil, okay, a current carrying coil which consists of multiple turns, let's say n turns, okay. We have n turns of wire and it carries a current I, okay. So here we have simplified this whole thing by considering a single turn of wire carrying a current I, and this is where we want to determine, at the center we want to determine the magnetic flux density. So here the magnetic flux density at the center of the current carrying circular coil is given by mu 0 Ni by 2R. So here for the single turn coil, this will become mu 0 I by 2R, and for this type of coil, so here there is 4 number of turns where it is, that will become mu 0 4I by 2R, okay. So as many number of turns, it will become mu 0 Ni by 2R. For single turn coil, it is mu 0 I by 2R. R is the radius of the coil, the distance from the center to the point, the circumference of the coil. Next is the magnetic field along the axis of a current carrying circular coil. Similar kind we have also discussed for electric field intensity. So here let's say we have a current carrying coil, circular coil of radius A, and we want to determine the magnetic flux density at a point P, which is at a distance x from the center of the coil along its axis. So here the magnetic field, again we have to divide this whole circular coil into small elements, small current elements. Here we have one, then again this, like this. We will keep doing it, and for each element we will determine small amount of magnetic flux density, and then we'll integrate it to get the total magnetic flux. So here the expression for magnetic flux density at point P due to the entire coil is given by mu 0 Ni A square by 2 into A square plus x square 3 by 2. So here these are the notations here. A is the radius of the coil, x is the distance along the axis from the center of the coil to the point P where the magnetic flux density is to be determined, and this is the thing. This is a single turn coil, so this n will become 1. So if there are more number of turns, this n value will be placed here. Next is magnetic flux density due to a solenoid and toroid. So let's say we have a solenoid or toroid, both consisting of n turns carrying a current I. So the magnetic field due to the solenoid and toroid is given by B is equal to mu 0 Ni. Okay, so these are some of the basic concepts related to magnetic field due to conductors, starting with Biot-Savart law. Then we discussed about Ampere's circuital law, and then the magnetic field due to very different types of conductors. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.